So a rational function is where we have a polynomial divided by another polynomial. And when we graph these, there are these places on the graph where the function doesn't cross. They're called asymptotes. And in order to really make graphing much easier, it's great to be able to figure out what those asymptotes are. So a vertical asymptote, just a definition here, a vertical asymptote is a place on the graph, it's a vertical line, where our function approaches, the output of the function approaches positive or negative infinity. So basically the function is just going way up, 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 or down towards negative infinity as it approaches that vertical line. So that's a vertical asymptote. And we can find these algebraically by simply looking at the denominator. They come up when the denominator is equal to 0, because then if we had x divided by 0, that's undefined, and that's exactly where our vertical asymptotes are. Okay, so we find these algebraically. We just go in and take our denominator, set that equal to 0. We can usually factor, or we sometimes need to use the quadratic formula, but on this one it factors as x minus 5, x plus 1 equals 0. And then using the zero product property, we get x equals 5 and x equals negative 1. Those are our two vertical asymptotes for this function. Let's look at another one. Here I would just look at the denominator. When is that negative, or when is that 0? And all you have to do is just solve that equation, and that gives you your vertical asymptote. So we get x minus 3 times x plus 1 is equal to 0, and by the zero product property we get x equals 3 is the solution, and x equals negative 1, and those are the exact places where we've got an undefined place on the graph. So those will show up as a dashed vertical line that our function can't cross. And let's look at this one. X squared plus 25 is equal to 0. So we've got subtracting 25 from both sides, we would get x squared equals negative 25, which has no real solution. So that means that there is no vertical asymptote. There's not always a vertical asymptote for rational functions, but that is how you find them if there are going to be vertical asymptotes. Okay, the other thing that's nice to be able to figure out on a rational function are the horizontal asymptotes, and those are just horizontal lines where our output is approaching some number. Okay, so let me show you how to find these. Basically, all we need to do is divide and look at the quotient. We can just ignore the remainder, but I'm going to show you why that works. So let's look at this first one. We have 3, and that's being divided by x squared minus 9. Okay, and I'm just going to rewrite this so that we've got x squared terms, x terms, and then we've got our 3. So when we try and take x squared divided by 9 and see how many times does it go into 3, well, the first step would be how many times does it go into your x squared terms, which is 0. So it goes in 0 times, and then we would take 0 times the divisor there. You get 0, subtract that, bring down your x, or just your x terms. It would go in 0 times, okay, bring down the 3. So you end up with a remainder of 3. The quotient, this 0, that is your horizontal asymptote. So y equals 0 is the horizontal asymptote. And what you'll find is if you have a degree in the numerator, in this case 3 would be like 3 times 1, x to the 0 is 1. So you can think of that numerator like 3 times x to the 0. And if this numerator is a smaller degree than the denominator, you'll get this same process where we just end up with zeros and the quotient is 0 with the remainder. So the horizontal asymptote will be 0 if you have too small of a degree up there in the numerator. Moving on. Okay, we're going to take 3x squared and figure out how many times you would take 3x squared and divide it by that divisor. But really it's the first step that we look at. The first step is you take your 3x squared and just figure out how many times would x squared go into it. So you don't really have to do long division. We're just taking the first term and seeing what is that, how many times does it go in there. So it would be 3, there is our quotient, and then 3, we would multiply that. 3x squared times 9 would be 27. Subtract all of that, so that means adding the opposites. You do end up with a remainder in this problem, but the remainder is, it begins to not matter very much as our x gets bigger and bigger, because if we write this as 3 plus this remainder, 27 x to the 9th minus 9. Well, as x gets larger and larger, what happens is this remainder starts looking like this. Like, let's say if our x was 100,000, you'd square it and subtract 9. That's a huge denominator. So if you're thinking of like, well, okay, if I had $27 and I'm sharing that equally among all of these people, down here in the denominator, we basically get almost nothing. And as your x heads off towards infinity, you're sharing your $27 with basically an infinite number of people. So you get nothing in addition to your quotient. This is what matters. There's the horizontal asymptote, because the remainder starts to be insignificant as x heads towards infinity. So there is, whoops, that should be a 3. Okay, so y equals 3 is your horizontal asymptote. All right, let's look at one more. 3x cubed. And there's probably going to be some remainder when we go through and do our whole division here, but it's really that first step that we care about that helps us with figuring out our horizontal asymptote. We look at the first division of the first terms. In this case, it would be 3x. So that would be the quotient, and there would be some remainder in this problem as well. But this is the quotient. That's the important part. So that would be the horizontal asymptote, but this is not a horizontal line. And so since it's not horizontal line, that means there's no horizontal asymptote. That's what's called a slant asymptote. And we're not going to do that in this particular class. You'll get that later on, but that is its own different kind of a asymptote. But this section is really just looking at horizontal asymptotes. So if you come out at the end and you have some equation that's not actually a horizontal line, then you know the answer is no horizontal asymptote. All right, so let's check our work. We can look at, I've graphed these functions. And you can see there's a horizontal asymptote here at x equals 0. And it's okay that the function crosses the horizontal asymptote right there at the origin. The horizontal asymptote is all about the end behavior as x heads towards negative or positive infinity. And you can see on this graph that it doesn't look like it will touch. And this, we also had a horizontal asymptote at x equals 3. So right there. And then you can see this is what a slant asymptote looks like. Not a horizontal line, but it's that diagonal line, y equals 3x. So I'm not going to give homework assignments like this with slant asymptotes, but you will have to graph when there's horizontal asymptotes. Now sometimes a function crosses a horizontal asymptote. It won't ever cross the vertical. So once we've found those, we know that is just the no man's land. That's where our function is undefined. The function's not going to cross that. But sometimes it does touch or cross a horizontal asymptote. So here's how we figure out those places. First of all, find the horizontal asymptote. Okay, so we take the leading term of our dividend and divide that by the leading term of our divisor. And that quotient, that is the horizontal asymptote. So y equals 2 is your horizontal asymptote. Now, to find if there's any touch points for crosses, what we do is we take our function and we set it equal to whatever we found for the horizontal asymptote. That's the y value there for the horizontal asymptote. Okay, so here we go, 2x squared minus 4 all over x squared minus 3x minus 4. There's our function. Set that equal to 2. I think the easiest way to solve these is to set cross products equal. So we'd get 1 times 2x squared minus 4, and that's equal to 2 times x squared minus 3x minus 4. And then solving, we need to distribute that 2. So we get 2x squared minus 4 on the left, and on the right we distribute the 2. So we get 2x squared minus 6x minus 8. We can subtract 2x squareds. I'm going to go ahead and add 8 to both sides. So I would get 4 is equal to negative 6x, and dividing by negative 6 we would get x equals negative 4/6, which simplifies to negative 2/3. So that's the touch point. And remember the y value at that horizontal asymptote, that we put in a y of 2. All right, there's our y. So the horizontal asymptote that has a y equals 2. So the touch has an input there of x equals negative 2/3. The y value is 2. So there's where it crosses or touches. Now, to be able to tell whether it's actually a cross or a touch, we need to put in some points nearby and see what the output is there. And we just need to start plotting points. So that's what I'm going to show in the next video. Well, let's get a sense. Where are we right here? Okay, so we had a horizontal asymptote at y equals 2. So as the horizontal asymptote is all about the behavior of the function as x heads towards positive or negative infinity. And you can see that that horizontal asymptote is what's happening as x heads towards negative infinity. But they're right there at x equals negative 2/3, it does cross. So there's sometimes some crossing and movement kind of close to the origin. The horizontal asymptote is all about the end behavior of the function. We can also see for this function, it looks like there's some vertical asymptotes. And again, the way we find vertical asymptotes is we look at when is the denominator 0, because that would create undefined function. And that happens here. If we factored this, we could solve where x is a positive 4 or a negative 1. Those are our undefined places. So there our vertical asymptotes are at negative 1. And as x is at 4. And there is our function. So now the next step is to actually take this information about asymptotes and touch and cross points and be able to come up with these function, the graph of the function. And that's what we'll do in the next video.